we begin really what's going to be one of the biggest units that we have in Cal 1 and one of the more consequential units that we have in Cal 1. So we spent the first half of this class really talking about what a derivative was and how to find it, and then we got into a couple of modules where we were using the derivative to make some predictions about our functions and try to tell what is our function going to look like. And we talked about using the derivative to figure out the velocity of an object and the acceleration of an object. And so we're going into this last unit, this last module, and we're talking about the antiderivative. So basically we are undoing all the things that we just spent doing, right? When we find a derivative, we take a function and we change it into a new function. Finding the antiderivative, we'll take that new function and turn it back into the old function. So we're going to talk a little bit about those as we go throughout this video. If you haven't found it, you might want to go to the Module 6 Introduction and look right down here. There is a table of integrals. Okay, so if you click that link, it'll bring up this table of basic integrals. That's something that's going to be extremely beneficial to you as you go throughout these sections. You also might want to have handy this table of derivatives. Excuse me, that one was doubled up there. So I'm going to go back to this Unit 2 here and pull up that table of derivatives. So having both of those handy will help us get through these units or these assignments that we have in the next couple of weeks here in this last module. Now, I'll have those handy as we go throughout this PowerPoint, just to make sure that that you know where I'm getting this information. Okay. So we're talking about the basic antiderivative, and here's just some notation things that you might want to be aware of. A function f is an antiderivative of the function lowercase f if the derivative of the antiderivative is equal to f. In other words, there's just, again, if I have 2x, right, then 2x is the antiderivative of x squared, right? So we would say that f prime of x is equal to 2x, and f of x is equal to x squared, okay? So just a little bit of notation. So moving into some of these, just some general statements about the antiderivative. F is capital F is an antiderivative of little f if for any constant c the function f of x plus c is also an antiderivative of f. So going back to that problem we were looking at just a second ago, if we have f of x equal x squared plus 3, and I say find f prime of x, well, that would be 2x, right? Well, what about this one? What if f of x were equal to x squared plus 31? Then we would still have a derivative of 2x. So the point of this slide really is, when we're working through these problems, the most general form of an antiderivative is going to look like this, f of x plus c, right? In other words, this arbitrary constant. Don't forget about the plus c when you're writing the answers to these problems. Here's one we'll take a look at. What is the antiderivative of 5 cosine x minus 3? In order to answer this, we need to think about, what did we take the derivative of to get cosine, right? What did we take the derivative of to get cosine? Well, we'll pull up that table of derivatives, okay? And here are some trig derivatives. We can see that we take the derivative of sine to get cosine, okay? So the derivative of sine is cosine. Well, in this problem, our function f of x is going to equal 5 times the sine of x minus 3, like so. Now, there are some tricks here. Like if this was an x squared minus 3, then it wouldn't work as directly as it does here. We're going to look at some of those more complicated functions as we go throughout this unit. So just bear in mind, what we really did was we basically asked the question, whose derivative is cosine. That's really all we were asking to figure out what this was, okay? And we can check ourselves here. I apologize. We can check ourselves just by saying, okay, the derivative of sine is cosine, so 5 cosine x minus 3, and it matches, right? Now, don't forget to put that plus c right there. We need to have that plus c in our solution. Here's one, 3 over x minus 2. So again, we want to go back to that table of derivatives here and say, well, what thing did I take the derivative of to get an x on the bottom? And you can just kind of scan. These are just some general formulas. Here's some trig stuff. It doesn't matter. Now, here are some things that look a little promising, right? I don't have a 1 plus x squared on the bottom, and I don't have any radicals. But if you recall, we have this guy, the derivative of the natural log function. Remember, the derivative of the natural log function was du over u. So let's go back and look at this thing right here. If I take the derivative of ln x minus 2, I get 1 over x minus 2. So if I wanted to end up with 3 over x minus 2, I would just have that constant out front. 3 ln x minus 2. And again, it's really just a matter of using that table of derivatives to try to figure out what function am I taking the derivative of to get this thing, right? There's a symbol we use, and it's this S-looking thing. Okay, so this S-looking thing means whose function has a derivative. I'm going to abbreviate here. Whose function has a derivative of f of x. Okay, so that's really what we're looking for when we see that little s thing. Now, generally speaking, we call that an antiderivative. Okay, the expression f of x is called the integrand, and the variable x is the variable of integration. So this thing right here, f of x, that's the variable of integration. Dx tells me what we took the derivative with respect to. So just remember, if you see this integral sign, you need a dx with it. Okay, so that s-looking thing is the indefinite integral. Now we're going to talk about a definite integral in the coming sections, but an indefinite integral will look just like this one here. When claiming that the integral, this is how it's read, the integral of f of x dx is equal to f of x plus c, it's important to check your statement, right? Make sure that if you take the derivative of this, it equals that. Okay, so that's a good way to check your answer. Find which function below is the antiderivative of 224 e to the 8x squared. Well, one thing we're going to do is we're going to recall that when we look at the derivative of e to the x, it's just e to the x. Now, one thing I don't like about this particular table is that it doesn't use the u's, right? So the derivative of e to the u is e to the u du. Knowing that, right? Knowing that the derivative of e to the u is e to the u du, that can help us figure out which one of these is going to be the right answer. I can eliminate d because I don't have e to the 64x squared here. So I know that my answer has to be A, B, or C. Now, what I want to do is figure out, where did 224 come from? Okay, so I'm going to do that by taking the derivative of 14 e to the 8x squared. So basically, I'm taking the derivative of each of these answer choices to see which one's going to work. I know that A is not going to work because there's an x right here. That would imply some type of product rule, which I don't have. If I take the derivative of 14e to the 8x squared, I get 14 times the derivative of e to the 8x squared, which is 16x, and 16 times 14 is 224. Now, we're going to talk in just a minute about some formulas we can use to find these antiderivatives. So in this one, really we just checked each solution. Okay, we check each solution to see which one is going to work. Okay, and that's really the long way to do this. There's a better way, and we'll get there. Here's one. We want to go in and look to see which function below is the antiderivative of this thing, right? Well, we're going to take the derivative of each answer choice to see. And taking the derivative of this guy using the chain rule will help us figure that out. So I'm going to start by taking the derivative of this outer cosine. And the derivative of that thing is negative sine. So I have negative 8 sine, and then what's inside remains. Remember, when we're doing the chain rule, we leave that alone. Now I have to take the derivative of what's on the inside, and the derivative of cosine 8x is going to be negative sine 8x, and then we're going to multiply by the derivative of 8x, which is 8. So I have this 8 here, and the 8 out in front, which is 64, and there are two negatives that multiply to give me a positive. Okay, so that is a very nasty chain rule. And again, the problems you're going to see in the homework aren't really going to work like this. What we're doing is establishing sort of the basis of how we get our answer. So in these, you're going in and you're checking each of these answer choices to see which one gives you this function here. Okay, so we're just checking these. We want to establish a way of finding the antiderivative without having to guess. Okay, and there are a couple of things that we're looking at. So I want to skip to this slide right here, and I want to point out, if you have to take the antiderivative of x to the n, okay, think about when we took the derivative of, let's do this, the derivative of x to the 5th. Remember, the 5 would come down, and we would subtract that exponent by 1. So instead of multiplying by this exponent, we're going to be dividing. If I'm going backwards, right, I'm finding the antiderivative, I have to go backwards. So instead of multiplying, I'm going to divide. And instead of subtracting 1, I'm going to add 1. So if I wanted to know what is the antiderivative of x to the 5th, then I would divide by whatever I get when I add 1 to that exponent. Okay, so it's x to the 5 plus 1 over 5 plus 1. Let me show you how that works in a couple of these problems here. So we'll start with this one. We're going to break this up into 3 different integrals. So I have the first integral in yellow, and then red, and finally green. And then we've got this one right here that we'll do in blue, this negative 3, okay? So I'm going to have the integral of 5x to the 3rd. Well, remember, we're going to add 1 to that 3. Okay, so we're going to have 5x to the 3 plus 1 over 3 plus 1. And then we're going to have minus 6 times x to the 2 plus 1 over 2 plus 1. Plus 9x to the 1 plus 1 over 1 plus 1 minus 3. And this would be x to the 0 plus 1 over 0 plus 1. You may be wondering where the 0 came from. X to the 0 is just 1, right? So if I have x to the 0, it's just like writing 1. So 3 is just like writing 3x to the 0. On this next slide, we do one where we have a little more complicated stuff. If we finish this one out, I'm going to have 5x to the 4th over 4 minus 6 over 3x to the 3rd. Obviously, we could reduce that. Plus 9 over 2x squared minus 3x. And this would be my antiderivative right here. So we can break this thing up into smaller, simpler functions to take a look at. We'll try the same thing here. I want to go in and find the antiderivative, okay? So I'm going to have 7 on the outside and the antiderivative of x squared, and then 5 times the antiderivative of e to the x minus 3 antiderivative of x squared sine x. So all they wanted us to do was express it in terms of simpler integrals, and we don't have to actually go in this problem and find out what the antiderivative is. But if we were to practice that power rule right there that we saw, this first one would be 7x to the 2 plus 1 over 2 plus 1, or 7 over 3x to the third. The one with the e to the x, the antiderivative of e to the x is just e to the x. Well, how do you know that? If I go over here and look at that table of derivatives, I took the derivative of e to the x to get e to the x, right? So that symbol means what did you take the derivative of to get e to the x? Now this one is a much more complicated antiderivative to find, so I wouldn't mess with that one right now. I would just help you focus on those simple problems where we're using this thing right here, okay? And here's one where we illustrate that again. So we're going to have 8x to the fifth plus 6x squared minus 4, and I'm going to take the antiderivative. Now let's focus in on this minus 4 right here. So that's going to go to minus 4x, because remember, this is like saying x to the 0, 4x to the 0. I'm going to add 1 to that, and I'm going to put that over 0 plus 1. So we get 4x. Right here, I'm going to add 1 to 5 and put that on the bottom. So I would have 8x to the 6, because I'm adding 1 to 5, over 6. This reduces to 4 over 3. So 4 over 3x to the 6th. Right here with 6x squared, I'm going to have 6x to the third over 3, right? 6 divided by 3 is 2, or 2x to the third. And this is my general antiderivative. Here's one that you can look at on your own and take a few minutes to see if you can get that problem. It's again, these are probably going to be most of the ones that you see in the Newton homework. I would like to point one problem out to you that you might see, and it looks a little bit like this, the antiderivative of e to the 2x. Okay, so if we had to do the antiderivative of e to the 2x, you're going to end up with 1 over 2 e to the 2x plus c. So the idea there is that the antiderivative of e to the bx dx is 1 over b e to the bx plus c. And again, you might need that rule as you look at a few of the problems in the Newton homework for this section. I know that was a lot, and it seems like it was rushed. The idea, though, is generally you're trying to find the antiderivative. In other words, the big question is, what did you take the derivative of to get this thing right here? What did we take the derivative of to get this? All right, good luck in this homework assignment. Let me know how I can help.